This is Dave Kroll from Imagine That. This is another episode of our masterclass series where we bring in people both from Imagine That itself, or ourselves, and the outside world, talking about various simulation topics. Some of the topics are general simulation, some are specific to ExtendSim. This one kind of bridges the two. This is reliability modeling, but it does use ExtendSim as an example. So today I have Anthony Nastasi, who's a simulation engineer here at Imagine That. He received a Master's of Science degree in Regulatory Economics from the University of Wyoming. Anthony designs and develops a variety of components of ExtendSim, including equation-based blocks, item properties and their structures, and most of the blocks in the item library. Before joining Imagine That, Anthony worked at Los Alamos National Laboratory modeling textile and supply chains. So with that, I'll turn it over to Anthony, and I hope everyone enjoys the session.
Hi, welcome to the Imagine That Masterclass on Modeling Reliability with ExtendSim. My name is Anthony Nastasi, and I'll be your presenter today. I've posted my contact information here so that I'd very much like to encourage you to contact me if you have questions or if you have ideas on how we can improve ExtendSim's reliability modeling capabilities. Also, if it wasn't already obvious from the title, this talk is going to be very ExtendSim centric. It's not a general talk on reliability, but rather how you go about modeling reliability with ExtendSim. So I thought I'd start with a Dilbert comic strip that echoes what we sometimes hear from our customers, that often the limiting factor in reliability analysis is not the modeling software, but rather access to adequate reliability data. Historically, that's certainly been true, but this may be changing. As Esther notes here, the proliferation of microsensors is going to change what kinds of data we have access to. So it's possible and maybe even probable that tools like ExtendSim will more frequently be applied to the study of system reliability in the future, and if that is true, then maybe discussions like this become more relevant. So looking at the agenda, we'll start with a very basic reliability overview. It will be very brief, but hopefully it'll help serve to get us all on the same page and provide a roadmap for the remainder of the discussion. Second, in terms of ExtendSim's current reliability modeling capabilities, we'll briefly discuss distribution fitting software and what role that plays in reliability analysis. Also, we'll take a look at two different modeling approaches in ExtendSim, the block-centric approach versus the item-centric approach. In terms of the block-centric approach, obviously, if you're familiar with ExtendSim, you'll know that the shutdown block can play a key role here. So with this block, we'll be exploring how to think about it in general, what roles it can play in reliability modeling, how it can interact with other blocks in your model, what some of the dialog options do, and also how it can be applied in various situations. So hopefully one of the things you'll get from this discussion is maybe how to get the most out of the shutdown block. In terms of the item-centric approach, we'll look at fleet reliability, a fleet reliability model actually that was developed by Robin Clark. In this model we have planes that are represented as items now, and it's these items that can fail. And then finally, we'll look at how you can build reliability block diagrams, or RBDs, in ExtendSim by basically aggregating the shutdown block with a combination of other ExtendSim blocks and then wrapping them up into H blocks, like the model you see here on this slide. The reason we're going to do that is it's going to help shed some light on our current developments for the next release. We're going to be coming out with an RBD library. And then the other thing is exploring this RBD model will give us a chance to see the different ways in which the shutdown block can be applied. So I saved this part for last because getting into that nitty-gritty detail of the shutdown block may not be something that everyone's interested in. So if you're not at that point, please feel free to exit the talk. Okay, so starting with a brief overview, the subject of reliability has been broken down into 3 categories: reliability, availability, and maintainability, aka RAM. Unfortunately, that term reliability is overloaded here, but with respect to reliability as a category, that simply means the probability of something failing during some interval of time. And the availability then is a measure of the readiness for something to perform. So readiness is the key term there when you're talking about availability. In terms of maintainability, it obviously includes concepts like preventive maintenance, but also wrapped up into the maintainability category is how a failed component or system can be brought back to a state of readiness. In other words, the repair process is also part of the maintainability category. This then begs the question, is ExtendSim a RAM modeling tool? More specifically, is ExtendSim AT a RAM tool? The short answer is yes. However, it's a little more complicated than that because ExtendSim is not a dedicated reliability modeling package. Rather, it's a general purpose simulation tool. Consequently, if you're using ExtendSim, you sometimes may need to go to another application in order to take advantage of RAM-centric bells and whistles. For example, the graphing capabilities designed and dedicated solely for reliability analysis are not included in ExtendSim. That said, the more complicated your system is, or the more your system deviates from some predetermined script, the more ExtendSim's open-ended modeling architecture begins to shine. So in terms of ExtendSim AT, we can map StatFit or maybe some other data fitting package to the reliability piece. We can map the shutdown block and or items to modeling the availability piece, and we can map ExtendSim's libraries in general to the maintainability piece. Looking at the first category, reliability, there are dedicated reliability tools which traditionally will do something called life data analysis. And while fitting tools typically do not directly support this, they do allow you to fit your reliability data into distributions that have been specifically designed for simulation software. And it's important to note that without this kind of distribution fitting, the application of ExtendSim blocks like, say, the shutdown block would essentially be rendered ineffective. So it's kind of hard to overstate how important these distribution fitting packages are. Okay, so assuming you've got your data fit, your data fitted into some good distribution, the next step is to apply these distributions to certain blocks in ExtendSim where we can begin to model the availability and the maintainability pieces of RAM. So looking at the maintainability category, looking at the availability category, here we have the shutdown block sending a not available signal to the activity's SD connector. So when that signal is true, the activity shuts down. But the question then is, what would cause the shutdown block to report a not available signal? Obviously, failure is one factor affecting availability. You can see here that in its simplest form, the shutdown block allows you to specify distributions for both time between failure and time to fail. And tying this back to the previous slide, the distributions you choose here would most likely have come from your distribution fitting software. But are there other factors that affect availability? Yes. So maybe a second factor might be off-shifting, right? For example, when workers go off shift, you might want to shut the activity down. If that's the case, you have the option to link the shutdown block to a shift so that when the shift goes off, the shutdown block outputs a not available signal. Another availability factor would be scheduled maintenance. If that's needed, you have the option to send a true signal to the shutdown block's SCED or SCED connector. When this happens, again, the shutdown block outputs a not available signal. So what are we doing here? Why are we integrating failures with off-shift and scheduled downs into one block? The answer is that these factors are often not independent of each other. So for example, when off-shifting occurs, the shutdown block will by default automatically halt its current progress towards its own next fail event. When you come back on shift, progress towards that next fail event resumes automatically. Similarly, the same thing happens with maintenance. A maintenance event causes the shutdown block to halt its progress. But in addition to that, once the maintenance is completed, you now have the option to have your scheduled downs, your TBF and your TTRs reset, which a lot of times makes sense. After a maintenance event, the likelihood of a failure becomes put off to sometime further into the distant future. So basically, the shutdown block can integrate and manage failures with shift and maintenance information in order to supply one overall availability signal on its output value connector. That's an important point to make because when you're working with the shutdown block, 90% of its interface has been dedicated to the various ways in which you can configure the TBF and the TTR. But as we see here, the block's more dedicated towards providing an overall availability signal and not just fail events and repair events. A couple of things to note here is that the title of this slide is not completely accurate because elements of maintainability are present here as well. In addition to the preventive maintenance signal coming in on the SCED connector, the repair process specified by the TTR distribution also falls into that maintainability category. We should also note that by definition, when you're using a distribution to represent repair, that means you're essentially black boxing the repair process, which brings up another question. What if you can't get away with just black boxing the repair process? Well, you might do something that looks like this, where the repair process has been broken out and modeled into an H block. Okay. First thing to note is that in the previous slide, the availability signal came directly from the shutdown block's output value connector. But in this slide, that's no longer true. Rather, here the shutdown block has been reconfigured to generate items instead. Okay, so what does that mean? What does it mean to be generating items in this context? Well, here the items represent fail events. And when the shutdown block generates one of them, it gets routed through the gate block and into the repair process H block. The gate has been set up here to do area gating, but we're actually not really using it to do gating per se. Rather, we're using the gate block's pound or number connector to help us understand how many items currently reside in the repair process area. Okay, so if we are currently in the middle of a repair, the number connector reports a value greater than 0, which results in two things here. Okay, the first is that the shutdown block's progress towards its next fail event is frozen because the SCED connector has received a true signal. So that scheduled down freezes the shutdown block. And then the second thing is the activity shuts down. If you have any questions about how that's working, send me a message, and maybe me or one of the other panelists can help out with that. Okay,
hey,
so
Anthony,
something else to note here is that yes.
Um,
Yes.
if you could just provide a definition of what TBF and TTR are briefly, as kind of a baseline.
Sure. TBF stands for time between failure. And so if you start off the model and you're in an up mode, you might specify, my time between failure is going to occur 5.327 time units from now, at which time you have this event, this fail event, and in the previous slide you would output a not available signal, or in this slide you would generate an item. That's TBF. TTR, or time to repair, is merely the time it takes to recover from that failure, to bring yourself from the fail state back to the readiness state. Okay, so something else to note here is that the concept of availability has been limited to repair only. But if we wanted to add other elements of availability to this, I'm sorry, I got a little thrown off. Okay, so at this point, the only element of availability that we're talking about is the repair process. And in this slide, we've broken out the repair process into an H block, and in that H block, you can bring all of ExtendSim's modeling capabilities to bear on that fail item. Okay, so if you needed to model the availability of repair tools or repair personnel, you could have the item sit in that H block and wait for those scarce resources. If you needed to wait on replacement parts, right, you could grab that out of inventory in this H block, and or wait for spare parts to arrive. So the whole point of this slide here is to show you, if you need to break out that repair process into more detail, this would be one way to do it. But there's something missing from this slide that we actually had in the previous one, and that is we modeled the availability signal in the previous slide with three elements: with failure, scheduled maintenance, and off shifting. And in this slide, we're only showing you the repair aspect of that availability component. So if we wanted to break out the repair process and also bring in other elements of the availability category, we could do something like this. So here availability is being represented again by the failure, maintenance, and off-shifting components. In this case, a true signal from any one of these three factors would result in the activity going down and the shutdown block freezing progress towards its next failure. So we're taking advantage of this little SCED connector on the shutdown block to field multiple sources of down, okay, multiple sources of not available. So that covers the block-centric approach to modeling reliability with ExtendSim. The next thing we're going to do is we're going to shift to ExtendSim and look at an item reliability model that was built by Robin Clark. Okay, so in this model, from a sort of high-level view of this model, we're creating planes here, and then planes progress into a queue where they wait to go on a mission. And after a mission is completed, the plane, which is an item, has an opportunity to have parts fail. If no parts have failed after the mission was completed, we just route the item, the plane, back, and it it proceeds on another mission. However, if some of the parts failed on that plane, two things are going to happen. First is we're going to spawn or create items that represent each part that failed, each component that failed. So if we had 2 components fail, we'll generate 2 spawned items here. And those spawned items will actually come down here and go into a repair process. The second thing that's going to happen is after we've created our spawned failed components, we're going to route the plane into this queue equation. And items in this queue, planes in this queue, will wait until all the components that failed have been repaired. Now, to understand how this model is really working, we have to look at the database just for a little bit, because it's a database-driven model. So here's the database, and the table that we're mostly interested in is this aircraft table. You can see here in this table that we've got, in this simple example, 5 airplanes, okay, and each airplane has 5 components. So a record in this table represents a component on a particular airplane, a particular component on a particular airplane. And we've got 5 components and 5 airplanes. This table also has a probability of failure for each component. The table also shows us what the current status of a particular component is and when its last fail time was. Now, this is a very simple looking table, but I hope it's apparent that because this model has been developed through the database, we can expand the complexity of our fleet relatively easily. Okay, so we don't have to make any changes to the model structure over here if we wanted to increase the number of components for a particular plane to, say, 10,000 components on a plane, and we don't have to make any changes to the model if we want to, say, increase our fleet to maybe 5,000 planes or something. So all that's captured within here, but the basic model structure stays the same. Oh, excuse me. Okay, so going back to the model, what happens then is when an item completes its mission and it goes into the query block, the query block will recognize what plane this is and recognize which records in this table it needs to sample for whether or not that particular record has failed. Okay, and essentially what we're doing in the equation is we're calling random real, which reports a value between 0 and 1. And if this value here is less than the probability of failure for a particular component, then we know we have a failed component. Once we have a failed component, we generate a spawn. And when we generate a spawn, we assign 3 attributes to that spawn. One is the aircraft ID, the other is the part ID, and almost most importantly, we're also storing on that spawned item how many spawns we're making, how many parts failed. So a spawn comes out of here, goes into the repair process. It's assigned a record ID in the log table. That's this guy right here. And then we log the time that the component failed. Then we send it through some kind of repair process. And then we log the time that the component was repaired. We basically reset the status from bad, failed to good, and then the spawn sits in here. The component part sits in the queue matching block and waits for any other failed items that may have come with it. Right? So if we generated 3 spawned items for a particular plane, then we'd wait here for the 3 spawned items to finish their repair. Then we batch up the 3 components into one item, and send a signal to the queue equation block that says, this is the plane that just got fixed, you can now release it. And then that item is released and goes back into availability for missions. And here I'm doing a little availability calculation. If you have questions, send me an email or call me. I can tell you more about how this model is working. So that's sort of one way in which you can do item reliability in ExtendSim. These are the items that have been modeled to fail and be repaired. Okay, so finally, the last thing I thought I'd do is take a peek at this RBD, reliability block diagram concept or idea. And basically this H block is providing an up or down, available, unavailable signal to the activity here. Okay, and if we look inside this, we have an H block that's just made up of a number of other H blocks. And each one of these H blocks represents either one component or any number of components. So this green guy, B, C, D, E, F, these all represent one component. This guy here, you could argue maybe represents 5 components or no components. I think you could say this one represents no components. This one, load sharing, basically K of N here basically says if I've got 3 of these 5 input signals reporting up, then we're in a state of up here also. But I'm getting ahead of myself. Load sharing, you can have any number of components that share the load, and in standby, you have some components waiting on standby in case some other component fails. And then here, we're representing any number of components in serial, and here we're representing any number of components in parallel. So how is this working? This block is always sending an up signal on its output connector, which means that these 2 blocks here, these 2 components, have the option to fail. Because this is an up signal, this guy is going to be up until it fails. If this were to report a down signal, the down signal from here would automatically get reported to this component and so on. So if I had this block always reporting a down, then the end result is that down signal would ripple through this web of components, and a down signal would be reported here 100% of the time. So essentially, what this block here is doing is it's monitoring what percentage of the simulation runtime this web of components is in the up state. And if you look inside here, you can see where we're looking at system. System in this case is this web of components. This is the percentage of time that this system was available to do work during the simulation run. So for basically 15% of the time, this activity was available to do something. The other 85% of the time, this block was frozen, was shut down. So how am I doing this? Inside here, I'm just configuring the shutdown block in different ways. So for a single component, if the signal coming into me is up, then I don't do a scheduled down, and this component now has an opportunity to either fail or propagate an up signal. If the signal coming in here is down, then we have a scheduled down, and this block will always report a down. And in this fashion, the up signal gets propagated through this web. If we look at these 2 blocks versus these 2 blocks, these guys are in serial, and these guys are in serial. But together, B and C versus D and E represent something in parallel. So serial means if this is down, if this fails, then this reports a down signal, and a down signal goes to here. But if both of these are up and a true signal is reported to here, then F will also report an up signal if F itself has not failed. Okay, so F only needs one true signal coming from C or E in order for it to have an opportunity to propagate an up signal downstream. So we say these two are in signal and these two are in signal, but together B and C are in parallel to D and E. If B and C are in serial, if one of these fails, then the net result is a down signal coming out of here. We're doing the same thing here with as many. In this case, we're doing 6 components in serial with one block. And we're able to pull that off with the shutdown block with just one block because we've connected the shutdown block to a database table. And the database table happens to have 6 records in it. And each record represents a different component. And through the dialog of this block, I've said I want all these components to be dependent upon each other. So if one of these records fails, then the net result is an output signal that is down. Okay. As opposed to what we might be doing here in this block, which is in a block that's been set up in parallel. In this case, I've got 3 components in parallel. And again, I've got one shutdown block with this time 3 records attached. And I'm using this OR block to say if any one of these 3 components is up, then I will propagate an up signal. So that's something you can do if you link your shutdown block to a database table. This is a little more complicated. Basically with standby, if the first component is up, then these 2 remain offline or down, and we end up reporting an up signal. If this guy fails, then I'll bring number 2 component online and report a net output of up signal. If both of these fail, then number 3 comes online. If all 3 fail, then we end up reporting a down signal out this connector. Here with load sharing, this is a little more complicated. Again, we've got, in this case, 3 components, but all 3 components are running at the same time. And if all 3 components are running at the same time, the load on any one individual component is as minimal as it can be. But if one of these fails, then the load on the other 2 components starts to grow, right? And how I'm using the shutdown block in this case is depending on how many components are up or down, I dynamically during the run re-specify what the TBF is through this lookup table. So that's a way you can do load sharing with the shutdown block. And then the last element that I haven't discussed here is the K of N, and we're simply just saying if at least 3 of the 5 input signals are reporting an up, then we won't have a schedule down here, in which case this component has an opportunity to fail or be up and running. So at the end of the day, what we're planning on releasing with the next version of ExtendSim would be a reliability library that directly supports the modeling of these kinds of systems where you have a web of components that are all dependent on each other for some kind of overall reliability signal into the system. And that puts me at 32 minutes for the presentation. I was shooting for 30 minutes and I went over 3 minutes, so that's pretty good. If you guys have any questions now, please feel free to ask, or if anyone has any comments from the panel, please feel free to open up the discussion.
Thank you, Anthony. Actually, John Maurer had a question that I thought was good. Well, let me answer. We just had one question pop up, so let me answer that. Ask this of you first. What about modeling reliability in the rate library?
Ah, good question. If I had time, what I would have done, and maybe I should have anyway, is if we go to the rate library, if I had time, I would have shown you the valve block. Okay, so here's the valve. And the valve has a rate a maximum rate connector. So we can integrate that with, again, the shutdown block this way. Now, by default, this block reports a true, right, when it's shut down. It's the shutdown block, so down equals true. That's a 1 or something like that. In the rate block, it has to be the opposite logic. So basically, when this shuts down, or when it fails, we want to report a maximum rate of 0. So what we would do is, in the shutdown blocks dialog, we would swap or flip these values. A down value is a 0 for a rate of 0, a maximum rate of 0, and an up value could be, if it's maximum rate, you might give this a very large number, right? And then the constraints on the system would limit what the effective rate was actually there. Or you might have some like maybe it's 10, right? I don't know.
And actually, I believe that Cecile showed me the other day that she's adding a down connector for the next version, a shutdown connector to the valve block as well. So in the next version of ExtendSim, and if anybody's interested in testing a prototype, that might be available. I can't promise for her work, but we're adding additional capabilities in so you can do it now. We're adding a little bit extra in the valve block for the next version. Yeah, the question is, what if you've already got something connected to the rate in connector, such as a rate from the database?
Okay, so if you've already got something in there, right, you might have to do something like, okay, so from the database. So let's go to the value library and grab a read block, right? So we're reading something from the database here. And there may be easier ways to do this, but the first thing that comes to mind is maybe I would do something like this with the equation block. I'd have 2 inputs, and this would be a down input connector, and this would be an up, maybe an up rate input connector, something like that. And then the output connector would be just rate, right? And you'd write an equation. Oh, yeah, let me get rid of this. And you'd write an equation that effectively managed these 2 signals. And you'd say, okay, well, if I'm down, then I'm just going to override anything that's reported on this connector and set this value to 0. If I'm not down, then I'll get my rate from the database. And that's, I don't know if this is too much detail or if this is obvious, but
No, I got a thanks on that.
If then else logic. Oh, okay,
Yeah,
so we're good.
Yeah, no, I think that's appears to be a good answer. Another question that came up, which is, in load sharing, does losing a resource cause the TBF to be shorter? Does the TBF restart from 0 or include time taken?
Okay, so in load sharing, what we have here is some basic concept, some basic implementation where all I'm doing at this point is I'm making a TBF dependent upon how many components are currently up. Now, if we wanted to do something a little more complicated, you should definitely feel free to contact me either through phone or email. But your question does raise something else that I didn't go into a lot of detail in the discussion, in the presentation, and that is anytime you are incorporating a scheduled down and down, or maybe if you have a shift. I don't have a shift in this model, so let me add a shift. And then let me reopen this. So now we have the ability to choose a shift. You also have the option to say, once I've gone off shift and then come back on shift, or once I've gone down and come back on, I have the option to pick up where I left off before the down event came, right? Or I can just ignore, right? I can just keep chugging through my events, my TBF and TTR events, and then once we're back up from a scheduled off, I'll just pick up wherever this guy happened to be, or we can reset. Now, I have not had any customers to date ask me to break this capability out into individual TBF and TTR pop-up menus. It's something I've thought about, and I may very well do that in the future. So make these two, and make the policies for TBF independent from the policies for TTR. If you think that's a good idea, let me know. I just haven't had anyone ask for it. So I hope that answers your question in part or in full, and I suspect not in full, but please contact me offline, and we can discuss how something like this might be enhanced to do something more substantial.
I got a thanks on that, Anthony. Robin, are you on? You had a comment that I thought was good.
On the shutdown block in the rate library, there is also an up connector that could be used to on the shutdown block. So you could feed your read into the up connector of the shutdown block.
Oh yes, Control-D, good.
Up value.
Yes. So yeah, that's a good point, Robin. I'm glad Robin knows my block better than I do.
Well, Anthony, I sympathize with you. It's hard to be put on the spot, and all of a sudden somebody asks you a question, how do you do this? And you think of a way to do it, so you go there. But there's often, sometimes there's a little better solutions, or certainly many times there's alternate solutions. So,
you know, sometimes I'm really surprised at how smart I really am. Because I did at some point add this connector to this block. I'm kidding, but that would be a much more elegant solution. Thank you, Robin.
Another question is, might you use the where input connector to handle TBF changes for load sharing?
Yeah, that's a good idea. That might actually work really well. Yeah, so essentially what you would do is, instead of breaking this out into 3 separate shutdown blocks, you could get away. You could dramatically simplify this, all of this, basically switch it to one shutdown block, and then the where is a calculated value. You'd want to switch this guy into multiple components mode, connect up to a database table for as many load sharing components you have, and then based on what is down, right, and you would want to go independent, and you'd link it, so you'd have, let's say you had 5 independent components, you'd have 5 output connectors that you would all feed into an equation value block that would then calculate what the where is and feed back into this where connector. Yeah, that's a good idea.
If you're half into your cycle and the where changes, does that speed up the last half of your cycle, or does that resample the TBF?
Okay, that would be, okay, so that would almost be a bit of policy, right? That would be captured in here, but one of the outputs, a second output to here would be obviously changing your TBF. You might have to use a combination of the two, right? There may be I don't know. Mathematically, I'm sure you could get away with just that and some tricky derivation here. You might, as an input, you would probably need to know how far along we've gone in terms of progress towards the next fail event. So this may not be as straightforward as a calculation as we might initially have thought. But one of the take-home messages from this presentation is you won't have to worry about that in the next release, because I will be providing one load sharing block that takes care of that for you. Right? This H block is going to turn into one load sharing block in the reliability library.
Anthony, I have a question. Does the where
Sure.
connector actually, is it just a 0-1 where, or does it actually take the value? For example, 2 would wear twice as fast as 1.
2 wears twice as fast as 1. 0.5 wears twice as slow as 1.
Cool. I hadn't thought about it in that context before. That's actually really useful.
And there are one customer in particular who actually may be present in this discussion from a company that will go unnamed. Worked with me very intensely for a couple of weeks, working out all the bugs if you supply a where value that's less than 1 but greater than 0. There were some interesting things I had to change in the code of the block to support that, to support a where value less than 1.
Another question that's come up. In designing highly available systems, it would be handy to allow the RBD net itself to be defined in the database and have the model automatically generated. One example would be a communication network. Any thoughts? I've done a lot of this kind of modeling.
You know, I'm so glad, whoever you are, I'm so glad you asked that question because this gives me an opportunity to show off my progress on this library so far. And it actually validates my intuition, right, that I needed to make the RBD library highly and tightly integrated with the database. So let me show databases here. Here I have a start node, right? And you'll notice that when I drag that start node on there, we automatically generated a table in the database. And it's going to be 2 tables, actually. A start nodes table, which will keep track of all the start nodes in the model. So now we should have 3 records in this table, right? Each record representing 1 start node. And then also, when we connect up components, to a particular start node, right, we can look inside this this start node block, and we can see this is start node block 0. And if okay, I'm out of space here. We can see all the components that are associated with this particular start node. Now, I'm gonna show off a little bit. I've worked quite hard on this interface. So if I want to use this interface to change, I don't want my database to be, you know, my start node block to be in the RBD default database. I'm going to change the name to this, right? Turns out you'll get a new database automatically with all the supporting tables that you need in it, and then you can change the start nodes table to whatever you want to call it, and in this database we will automatically have everything follow. So with this level, same for the components table, with this level of integration between block set and database, it won't be much of a trick at all to go the other way, to take a database that's been built in the appropriate format and automatically build out the blocks into the model. That may be coming in version 2. I can't promise that we'll go both ways in version 1 of this library, but the infrastructure is there to support that in the long term, for sure.
One more quick question I'll just answer for everyone's benefit is can the database tables be loaded from CSV format files? And the answer is yes. There's a couple different ways of doing that. Either the data import-export block or the there's a function that will just you can call it. We'll just import a CSV or comma separated value file, a text file, into a database table. So that's actually quite easy to do. Peter Turner says it's also interesting to include some Markovian solvers.
Yes. Okay. So another customer who's been very kind and very helpful has, let me grab, I'm not sure if this is what I think if your question is what I think it is, but we've had a customer donate to us a component importance block. And I may be heading down the wrong path in terms of Markovian whatevers, but this component importance block gives you a list of all of the components in your network, in your web, and lists them in order of how important a particular component is to contributing to the unavailability of that system. And I'm not. Is that related to your question? And if it's not, please let me know if there's something else that you were thinking of.
I'm not seeing anything else. So, Anthony, thank you very much. That was an excellent presentation, and I like the preview of what's coming in. I think a lot of people are going to be excited about that when it does come out. This should be in I think what we're going to call, it's not all set in stone yet, but probably be something like a 9.2 version of ExtendSim. Is that what we're targeting with that?
I wouldn't go that far.
Okay.
At this point.
Okay. It's still a work in progress, but it's something we're definitely working towards. A lot of this I know is based on the fact that people are currently using ExtendSim for this kind of analysis, so it's just taking them the next step further. So that was a quick preview of one of the many things that we're working on. So I don't see any more questions. So thank you very much, and I will we'll end the session. Thanks again, Anthony.
Sure.